Hi, welcome back to the lectures on GPU architectures and programming. So, in the last lecture, we have briefly introduced these concepts of OpenCL programs and we were discussing the OpenCL execution model. So, continuing that, we will slowly introduce the different OpenCL concepts one by one. So, what will come first is the OpenCL context. So, we are starting with the execution model of OpenCL programs. So, what is a context? So, essentially a context is nothing but an abstract container that exists in the host side and it includes the following resource definitions. So, it is like a object, I would say an abstract object, an abstract definition, and it is containing information on the following resources, that is first of all the devices, that it will contain the information about what are the OpenCL devices which are to be used by the host and how to access them. It will contain the different OpenCL functions that are to be run on the respective OpenCL devices, and it will contain these program objects. So, essentially what are program objects? The program source and executables that implement the kernel. So, you write a kernel, now from that kernel the OpenCL runtime system will build a program object, and then it will also contain the memory objects. So, the set of memory objects which are visible to the host and the OpenCL devices. So, in a nutshell, so we are trying to define how a OpenCL program's execution is set up. It is all based on this definition of a context, and the context captures what am I going to execute, which are the kernels which are translated into a program objects, and they are going to use data from again the memory model which is kind of known to the host in the form of again memory objects, and the devices like which are the actual SIMD architectures where these kernels will be executing. So, a context is something that gets created by the OpenCL API. Essentially you have to write a suitable host program and you have to call suitable functions from the underlying OpenCL API through which you have to actually create the context. Now, it is useful primarily for executing the kernels, getting their results back from the devices, using those devices for executing more kernels in other devices and all that. So, essentially the context inside, whatever coordination one will do, we understand from our basic knowledge in GPU programming now that the host device is actually responsible for orchestrating the execution of kernels in different GPU devices, right. So, coming to OpenCL, the similar concepts are actually going to hold. So, the host program, the host side code is actually orchestrating the execution of these kernel objects on different devices, but all these things are happening inside the definition of this context. It is also managing the memory objects, it is deciding which memory object is accessible to which device and all that. So, essentially the context is an abstraction which binds devices with programs and memory objects. Now, limiting the context to a given platform helps to fully utilize a system comprising resources from a mixture of vendor. Now, this is the useful thing, like why do we need the definition of a context? The primary reason is because of the OpenCL platform model. So, it may always happen that you have built a large compute system where multiple different kinds of devices coming from different vendors, let us say Intel, let us say AMD, let us say somebody else, they are all connected to the PCI Express bus, right. Now, let us understand that each of them may be OpenCL compliant vendors. So, what they will do is each of them will provide the underlying ICDs, installable client drivers conforming to the OpenCL specification, but they are all specific for each vendor, right. So, a collection of devices from a specific vendor, for them if I define a context, then that context will use that vendor supplied ICD for performing its execution. Some other context I will define for some other set of devices from some other vendor, right. And I can have the host program coordinate executions in different devices where each of the devices are mapped to different contexts, right. So, inside a context I have the memory definition, the device definition, the kernel definition and program execution going on. I can have another context where another set of kernels are executing, and the top level program can actually manage multiple contexts executing on different vendor supplied platforms, and it can help these different contexts communicate data among each other for performance benefits or getting more parallelization. So, the basic idea would be that you want to have an abstraction through which you can actually link up things from different vendors in a coherent way and still proceed with building something big. The next important concept here would be what we call as the command queue. So, when we are talking about context, as I said, it is basically an abstraction through which I am trying to define how an OpenCL program will look at the memory, how an OpenCL program will look at a device and all that. But there has to be a specific formalization that hey, the devices are going to execute this kind of commands in this specific order, and how will that sequence of commands coordinate among each other, right. So, for that, the top level host, let us understand the difficulty with the host. The host is trying to manage a set of devices. As I said, in the worst case, the devices can be of different vendors. That problem is solved by bunching out devices together into a set of contexts. So, the host has to manage a set of devices sitting in different contexts. Well, that is fine. But when the host is trying to dispatch some action for each of the devices, the host needs a mechanism for doing that. So, what the host does is it creates another data structure called command queue, through which it can submit instructions that to a device that okay, you execute a kernel, okay, you get this data back, okay, you use this data as an input. So, these are all elementary actions which a kernel will perform, which a device will perform, and in what order it will perform, that is orchestrated by the host through a command queue. So, all the host does is that it places commands to the command queue, which are then scheduled into the devices within the context. A device will have its own command queue, and the kinds of commands can be different. They can be kernel execution commands, they can be memory transfer related commands for the device, and they can also be synchronization commands. Now, these queues can execute both in order as well as out of order. The host can also specify that for some device, whether the commands that are queued up in the command queue of the device, whether they will execute in the order in which they are queued up or they can execute out of order. Now, so we have understood what is a command. So, essentially it is one of these following things like kernel execution, a memory transfer instruction, or a synchronization command. So, these are the different possible commands that a host can issue to a specific kind of device, right. Now, once this command is issued, it can go through the following well defined states that the OpenCL runtime system understands. So, a command will be queued, the command will be submitted from the device, it will be dequeued and submitted to the device, it is ready to execute, it is actually running, the command ends and the command gets completed, right. So, these are all the different possible status messages for a command under execute, which is in a from its lifetime when it starts sitting in a queue up to the point when it gets completed in its execution. Now, in the OpenCL execution model, the other important thing from our perspective would be synchronization. So, what is synchronization? So, we understand that in a data parallel program, we often will require threads to synchronize at certain specific points, which are the barriers, right. For example, in CUDA we had the sync thread construct, right. Similarly, in OpenCL, like we have thread blocks or work groups containing execution of work items, and work items will often like to synchronize among each other. So, the synchronization would refer in this case to mechanisms that constrain the order of execution between two or more units of execution. So, it is possible to do work group synchronization. So, this essentially means constraints on the order of execution for work items in a single work group. So, this is kind of similar to our idea of sync threads in CUDA programs. So, a sync thread would synchronize all the threads inside a thread block, but not across thread blocks. Here in this case, I can perform in similar way. I can synchronize work items sitting inside a single work group. The other notion of synchronization is comment synchronization. So, I can put such synchronization primitives inside the comment queue. As you can see that this is one of the possible commands that can be submitted by a host program in a command queue. So, I can give a kernel execution command, I can give a memory data transfer related command, and I can also give a synchronization command, right. So, when we talk about a synchronization command, that would mean a constraints on the order of commands lodged for execution. So, that would mean a suitable synchronization command will be enqueued by the host on the command queue, and it will restrict the order in which commands are going to be launched for the execution. Now, as we have been discussing that in OpenCL we defined an execution model and also a memory model, and so this is the picture of the memory model. So, you will have host memory, and so that is the host side memory and host side compute environment, which you have here. From the host you can copy data to the global memory of a specific context. Now, this is where things become a bit more complex and different with respect to CUDA. We need not have a single device, we need not have a single GPU. I can have a rather collection of devices. I can, among the collection of devices, I can have devices coming from different vendors. Accordingly, what I will do as a memory object, I will define a context as an abstraction. Inside this context, I will have a collection of devices. They are global and constant memory, and I will have this notion of work groups executing on the scalar processors or processing elements, right. So, work group will be constituting work items, and these work items will have access to their private memory, the shared local memory, and in the worst case they will also have to access to the global memory in the context. So, I can have multiple devices in the context. So, I can have a set of work groups executing together in one device, another set of work groups executing in another device, like that. So, to be more specific, what we have more here is the host can orchestrate execution across multiple devices, and those set of multiple devices can be again grouped into this abstraction of contexts. Now, coming to the memory object definitions. So, the contents of global memory are essentially open memory objects which use the OpenCL type CL_mem. Now, memory objects can be of the type buffer, which are stored as block of contiguous memory and used as general purpose object to hold the built-in types like integer, floats, other vector types, or any user defined data type in an OpenCL program, and they can be manipulated like through pointers, similar to any kind of memory block access that you can do in normal C program. The other thing is image. So, in OpenCL you have a separate memory type defined for images, which is useful for holding multi-dimensional images up to 3 dimension, and the formats are based on standard image formats. So, like you have support for different standard image formats. So, that is specifically provided targeting graphics applications, which was the original workload domain that was targeted, and they need to be managed by functions which are defined in the OpenCL API, which would mean whatever vendor provided ICD file you get as part of the OpenCL distribution on your processor, it should contain implementations of the required functions for reading and storing such image objects. So, if we do a summary here of the OpenCL memory model. So, from the global perspective, in the host you have support for dynamic allocation, you have read write access to buffers and images. From the kernel's perspective, you have static allocation for program scope variables and read write access, right. If you look at the constant memory segment, again from the host side you can do a dynamic allocation, you have read write access. From the kernel side you would have static allocation and only read only access from the constant, right. But so whatever has to be defined from the host side as constant. Now, from the local memory part, again for host you have a dynamic allocation, but from the kernel side you again have static allocation, but every thread can of course read as well as write in its the shared local memory of each of the compute units, and of similar behavior is also expected from the private memory for each thread. So, that is why you also have read write access in the private memories, right. Of course, for the local and the private memory which are in the device, right, because this is in the inside each of the compute units and this is inside each of the processing elements that are sitting inside the compute units. So, they are all in the device. So, the host really does not have any access to these memory segments. This is what is supported by the OpenCL kernels that are submitted to the respective devices. So, if we come to the programming model, so you have a data parallel model of OpenCL execution, where you define the computation in terms of a sequence of instructions that are of course applied to multiple elements of a memory object. So, that is how we have been writing usual C code using usual CUDA code, and the alternative is task parallel model, where you define a model in which single instance of a kernel is executed independent of any index space. So, this is also something we will look into, and of course, you have support for a hybrid combination of both these models. Now, in OpenCL you have support for a hierarchical data parallel programming model, which would mean in the explicit model the programmer defines a total number of work items to execute in parallel and how the work items are divided among the work groups. And you can also have an implicit model where the programmer will only specify the total number of work items to be executed in parallel, and the actual way in which the work items would be divided into the work groups will be managed by the OpenCL implementation. Now, this is important. This essentially means that as a programmer you can choose to explicitly specify the hierarchy of work items and work groups, or you can actually let the runtime system take care of that. So, that would be the implicit model. So, and this is logically equivalent to executing a kernel on a compute unit with a work group containing a single work item. So, this is more about the task parallel programming model. So, logically it is same as like executing a sequential task, and the parallelism is expressed by a vector data type implemented by the device, and you keep on enqueuing. You can just also enqueue multiple tasks. So, we are just introducing the names here, and we will of course focus on this later on. Now, coming to this OpenCL program structures, like how really OpenCL program is ordered into different parts, but for that we will first see that there are different subparts in a typical OpenCL program. The first part will define what we call as the platform API, and the second part will deal with what we call the runtime API. So, first of all, let us understand what is the platform API, because then we will see that how that is required to query the platform in the first stage of the OpenCL host program. So, in the OpenCL runtime system, you have a platform layer API, which is an abstraction layer for diverse computational resources, and the OpenCL, and as a programmer you have to use the query functions defined in this platform layer API for querying, selecting and initializing different compute devices. And using this API you can also create contexts and work queues. So, that is the high level API through which you have to actually create the different objects and abstractions like contexts, the memory objects, the program objects and all that. And also once all these data structures are up and running, then you will be using functions from the runtime API to launch the kernels and manage the execution of the kernels, schedule the executions of the threads across the different devices, and utilize the memory resources and achieve synchronization as and when required across the threads and all that, right. So, if we just try and understand at a broad level, inside OpenCL program, the first part would be to set up the data structures that are there, which will be managed by the platform API, and then to do the actual workload scheduling across the different devices, which is managed by the runtime API. Now, as we have been discussing in a OpenCL program, you will have a initial part which is the host program part and also the kernel part, and the host program part will have a set of different steps to execute, and this is kind of a much more, I would say, a bit more complex. Then a normal CUDA host program, where all you need to do is just define the basic variables and then define and set up the memory space for the GPUs and launch the kernels. The reasons are also something that we will discuss, but first let us understand what are the different steps that a OpenCL host program has to perform. The first thing it will do is it will query the different compute devices through the platform API and try to figure out the way the devices are arranged, they are from which vendors and all that. So, I mean the query phase, of course, I mean if you know your exact device and all that, you can write an OpenCL code which will not require to do this query and all that. But let us understand that we are trying to understand what is the generic way to write OpenCL programs which can execute on any OpenCL supported device. So, for that, initially the program that you write should be able to query the platform and get suitable values about its architectural information, which it will use for setting up the different memory objects and which it will also use to schedule the work items and all that. So, using this query phase, you are first learning about the parameters of the underlying platform, and whatever you learn, let us say the number of devices from different vendors and all that, that are useful for creating the contexts of execution as we have discussed earlier. Inside the context, you would next be creating the memory objects associated to the contexts, and then the next step would be to compile and create the kernel program objects. Now, as you can see, this is also a part of the runtime system. This is also supported by the runtime API, but these are all activities that are to be written in the host program itself. So, now this seems a bit weird that we are saying we have a program where we have first set up the context, we have queried the devices and set up the context, and now we are saying that okay, we will have further commands in the host program to create memory objects associated with context. That is also fine, but the next thing is we will have compilation commands in the host program for compiling the kernel code that is also going to come after the host program. Now, that is a weird thing, right, because till now we have been looking at things like we will write the code and then we will use a compiler to compile it, but let us understand here the compilation process is to be managed by the host program, and the way the program will be executed will be managed by the runtime system. So, the entire thing starting from basic compilation to setting up the memory objects and using these compiled kernels to issue comments to the comment queues, everything is performed by the host program. So, this makes an OpenCL host program a bit more complex, but at the same time the structure of most OpenCL host programs are very similar. So, once we are acquainted with one, writing another OpenCL host program is quite easy because most of it is going to be a copy paste job, but we need to understand what are the different steps. So, the takeaway at this point would be that the host program is not only responsible for declaring memory objects, declaring inside the content and binding them to context, but also for doing a runtime compilation of the different kernel program objects, right, and then enqueuing the kernel launch commands in a specific order into the command queues. So, that would also mean the host program is also responsible for defining the command queues in a part device manner and enqueuing the different kinds of commands like data transfer commands, kernel launch commands, synchronization commands, all of them in the command queue. And at the end of after that, the next step would be launching the kernels through the runtime system, and once the kernels have finished their execution and the results have been properly computed, to clean up the underlying resources which were the underlying resources that the OpenCL objects were occupying, right. So, this entire orchestration of compilation activity, memory object definition activity, command enqueuing activity, command execution activity, synchronization activities, and the final cleanup, this entire thing is managed by the OpenCL runtime system based on the query of the platform and the creation of context which is supported by the platform layer. So, these are the different phases through which a typical host program or an OpenCL host program would go through. And so, then the question is what is happening with the kernel? The kernel is a simple C-like program, right, with certain restrictions and extensions, and So, that would also be there, but the host program, I mean the point I was also trying to make multiple times again, I would say that the host program will be also responsible for runtime compilation of these kernel programs. So, today we will end with just a look on a look on a simple OpenCL kernel, which would be our most popular vectorAD kernel. So, on the right hand side I have a vectorAD kernel in CUDA, on the left hand side I have a vectorAD kernel in OpenCL. So, as you can see, like we discussed earlier, the global keyword in CUDA gets replaced by the underscore underscore in one side only, I mean the kernel keyword in OpenCL. And here you had the input parameters and the output buffer parameter and the size. Similar things you have A, B and C, right, but they also come with this global keyword in case of the OpenCL variables. If you go back to our earlier discussion, so when we are talking about this, we had this global variable declaration here, and that would mean that they will be defined in the device's global memory, right, and the output will be computed again in the device, each specific device's global memory, right. Now, coming back to the CUDA code, you see that the first item was to compute a global thread ID. So, this was our usual computation, I equal to thread ID x dot x plus block dimension dot x multiplied by block ID x dot x, and then based on the value of I being inside the range, you are computing a normal C statement, which is Ci equal to AI plus Bi. Look into here in the OpenCL code, the last two lines are exactly same, because fundamentally this is a C program which its own definitions of OpenCL types, data structures and runtime primitives. But look at the way I is computed. You simply have a call to something called a get global ID function. It's providing you the global ID value for this thread, right, the corresponding OpenCL work item, and the work item will will execute this addition for this specific value of I. So, that is one good aspect here. You need not write this line time and again, rather you just figure out what is the global ID using this kind of a function, right. So, you have similar functions like get local ID to get the ID inside the thread inside the work group, right, and so the global ID will give you the actual position inside the global arrangement of threads that you may have defined, and the 0 will signify that this is just in the first dimension that we are talking about, and this is not a multidimensional kernel. Now, if we write one or two things like that, we will be actually talking about finding out the global ID specifically in that dimension. So, in case you are trying to linearize a multidimensional kernel, there are additional OpenCL get global kind of commands which we will be discussing later on. So, with this minor introduction to writing OpenCL kernels, we will end this lecture, and in the next lecture we will look at the skeletal structure of a OpenCL host program. Thank you for your attention. We will get back soon. Thank you.